Hi, welcome everyone. Welcome to this class, to the fourth class of this discussions. So, in the last few classes, we discussed about the uh, velocity correlations functions. So, the velocity autocorrelation function was Vt prime. It was assumed to be this kb t by m e to the power minus t prime by tau v. Kb t by m e to the power minus mod of t minus t prime by tau v. Now let's calculate the mean square displacement from this. So xt minus x0 whole squared was 2 into 0 to t. So how to get to this? To understand this, let's discuss in the following manner. So the equation was, Navier equation was m dv dt was the Navier equation was m dv dt is equal to minus gamma v plus fr t, right? So from here we get this Vt was V0 e to the power minus t by tau v plus 1 by m 0 to t dt1 e to the power minus t minus t1 by tau v into fr t1. Now if you write, and this Vt is actually xt, this is x dot t is equal to Vt. So xt minus x0 will be 0 to t dt1 v of t1. Okay. Now if you squared it, then xt minus x naught whole square, then its average will be 0 to t dt1 0 to t dt2 v of t1 v of t2, this autocorrelation function. Now we know this autocorrelation function, this will be replaced by e to the power minus mod of t1 minus t2 by tau v into kbt by m. So we are writing this, so kbt by m 0 to t dt1 0 to t dt2 e to the power minus mod T1 minus T2 by TV. Okay, so this is this relations. Now to solve it, since there are two variable T1 and T2, so this is T2 and this is T1, and what will be the T1 T2 graph? So this line will be T1 is equal to T2. Now if we get this half, if we get evaluate this integral in this half, then this half will be same as this. So if we evaluate in this area, and if we multiply it by 2, then we will get the whole thing. So this equation, let's say 3, equation 3 is symmetric about T1 is equal to T2, T1 is equal to T2 line. Right. Okay. Just a minute. So basically what we are trying to so what we are trying to do here is getting or calculating that part. Okay. So now let me just a minute. It's just a minute. Some network issue. So you can get here. So now we have to do this line. So if we calculate the integral, now if we calculate the integral in the one half of this region and multiply it with a factor of 2, then we will eventually evaluate the integral. Now in this region is always T1 is greater than T2. So this function e to the power minus mod of T1 minus T2 by tau v, this becomes e to the power minus T1 minus T2 by tau v, because T1 is greater than T2 in this region. So there will be one 2 term here. So xt minus x naught whole square becomes kbt by m 0 to t dt1 e to the power minus T1, sorry, Let me write it. So there will be two factor here into 0 to t2 dt2 to the power minus t1 minus t2 by tau v. So 2 kbt by m 0 to t dt1 e to the power minus t1 by tau v into 0 to this is v, and so, and what will be the limit of t2 then? Limit of t2 will be 0 to t, because it can never, sorry, 0 to t1, because it can never exceeds t1. So this limit then becomes t1, because maximum it reaches t1, t2 maximum it can reaches from 0 to t1, right? Okay, so then it becomes 0 to t1 dt2 e to the power t2 by tau v. So this becomes 2 kbt by m 0 to t dt1 e to the power minus t1 by tau v into e to the power t2 by tau v by 1 by tau v limit 0 to t1. Okay, so this becomes 2 kbt by m 0 to t dt1 e to the power minus t1 by tau v into tau v into e to the power t1 by tau v minus 1. Okay, so now it becomes 2 kbt into tau v by m into 0 to t dt1. First it is 1 minus e to the power minus t1 by tau v. For 1 it becomes 2 kbt, tau v is m by gamma, so m cancels out, and for first term it will be t1 minus minus e to the power minus t1 by tau v by minus 1 by tau v limit 0 to t. So the for the first term it becomes 2 kbt by gamma for sure, and for the first term it will be t, and for the second term plus, for t it will be e to the power minus t by tau v by 1 by tau v minus 1 by 1 by tau v. Okay, so then it becomes then, right, there is no problem with this. So 2 kbt by gamma t plus tau v times e to the power minus t by tau v minus 1. So this is equation. Now depending upon this constant tau v, we can get two different regimes. Okay, so first it's called ballistic regime, where t is less than tau v, means if we get at a time scale very less than autocorrelation time, then equation 4 becomes equation 4 becomes 2 kBt. So if that is the case, then this expression t is very greater than, so e to the power minus t by tau v. So before that, so that means t by tau v is very less than 1. That implies e to the power minus t by tau v is 1 minus t by tau v plus t square tau v square. Okay, so if you substitute that into this, then you get xt minus x naught whole square is equal to 2 kBt by gamma is equal to t plus tau v times, if you replace this, minus t by tau v plus t square tau v square minus 1. So this cancels out, and this term will be cancelling this term. So this becomes 2 kBt by gamma is equal to t minus t plus t square by tau v. So t cancels out. Now you can easily see this becomes 2 by kBt into gamma tv into t square. So it is varying like ballistically, or like quadratic power of t square, or you can write more like this, 2 kBt. Okay, so there will be t square tau v square 2 2 2 2 cancels out, so it becomes kBt by gamma into m by gamma into t square. So gamma cancels out, and become kBt by m t square. So here, if you think about the time scale, which is very less than the autocorrelation time, then you get a ballistic regime. Okay. Now let's assume another thing is when our time scale is very greater than tau v, that autocorrelation time. That means that when we are, so in our normal or observation time scale, which is around millisecond, there t is very greater than tau tv, so then t by tau v is very greater than 1. That makes e to the power minus t by tau v very greater than 1, so tends to infinity, so it will be to the power minus infinity. So that makes it tends to 0, right? So t by tv, so here if you see here, it tends to 0, that makes it tends to 0, right? And tau v is also small, so you can write then x t minus x naught whole squared average is equal to 2 kbt by gamma, 2 kbt by gamma into t minus tau v. That will also becomes 2 kbt by gamma into t, because t is very greater than tau v. So that makes our MSD, or mean square displacement, xt minus x naught whole square becomes 2 kbt by gamma is 6 pi eta a into t, and which is nothing but 2 dt. Okay, so or you can write at that. Okay, so here mean squared displacement varies linearly with time. So that's why in real experiments we cannot see that if you plot the mean square displacement of a Brownian particle, we always see it grows linearly. Never it grows, ballistically. So that explains this thing. Now there is one important thing in this discussion is the how to calculate the Stokes drag. So for that I will derive it for a spherical particle. Okay. So for a spherical particle I will derive a Stokes drag on a sphere. So Stokes drag on a sphere. Okay. Okay. So this is a pure fluid mechanics, and in software matter system we have to see and different kind of fluid mechanics is involved there. So first we will assume that we are assuming the low Reynolds number regime. That means Reynolds number is very less than 1, or viscous force dominates inertial force. Or in other word, gamma v is much greater than m dv dt. Now let's say this is a spherical particle and there are two like this. Okay. Now let's say its relative velocity with the fluid surrounding it, the relative velocity of this particle is v. Then the Navier Stokes equation Navier Stokes equation in vector notation becomes like this. So we will use a certain coordinate system. So this becomes rho du dt plus u du dx plus v du dz dy plus w du dz is equal to, I will explain the terms, minus dp dx. So this is for one component, plus eta delta u del x2 plus delta 2 u del y2 plus delta u del z2. So this is a x component, this is x component of momentum equation. So what is that equation? That equation is v, so rho du dt plus v dot grad u okay. So this is a vector v is equal to minus grad of p plus eta Laplacian v. So v has three components, u, small v, w, okay. So this v is different, this is a capital V, let's say this is a capital V, okay. So in that way this is equation 1, this is equation 2. So in that way what will be the this relative velocity is capital V, let's say. What will be the first y component? So the y component of momentum equation will be rho, so v's y components is v, small v, so dv dt plus u del v del x plus v del v del y plus w del v del z. So that is this thing, and here this will be del p del y plus, for this one this will be eta del 2 v del x2 plus del 2 v del y2 plus del 2 v del z2, okay. So here one important thing is no body force is considered, okay. So for the z momentum equation will be compact notation momentum equation in compact notation will be rho dw dt plus capital V grad W is equal to minus dp dz plus eta nabla omega. Okay, so if you want to add, so you can add a body force like this. So but this force is not, we were not required like in this discussion. So this is not required. Okay, so that P is body force. Okay, now so from equation 2, if Reynolds number is very less than 1, we can drop the left hand side of equation 2. So we can drop this whole chap. Okay, so if you drop that, then the equation becomes, then the equation becomes then the equation becomes minus grad P plus eta nabla square V is equal to 0. Remember, this is a vector equation. Now if you take also here, it's an incompressible fluid, incompressible fluid is assumed, so that makes zero. Okay, so if that is 0, now if you take, so this is 3, this is 4. Now if you take curl of both sides in equation 3, that becomes, so this will be 0, curl of gradient is always 0, so 0 is equal to eta curl of nabla V. Now curl of gradient is 0. So now for this relation, if you know, we know this relation, right? We know from vector calculus that if you take curl of V, then it becomes this one of this minus square V. So since this is 0, so this becomes this, right? So where where curl of V is called vorticity. Vorticity. Okay. So then we can write this way, that this one of this is 0. Why? Because from here if you take curl, then this will be the same as eta curl of this guy. So now this is replaced by this, right? So that's what we were writing. Now from this chap we can easily write as gradient of divergence of vorticity minus Laplacian of vorticity is equal to 0. From this it follows vorticity, if you take this, so here what I have done is we have taken curl of both side and it's become this, and with this chap, this Laplacian, that becomes curl of V, and curl of V is this guy. So that's what I have replaced. So there is minus, so that doesn't matter. Okay, now this chap is also 0. Why? Because divergence of curl of a vector is 0. Divergence of curl of a vector is 0. So then it becomes only Laplacian of this is equal to 0. Only thing remains is this. So if we take a 2D flow, this is 4, this is 5. If we take a 2D flow, then Z component of vorticity will be delta V of, let's say, first write it. So this will be curl of V, its Z component, that means delta V delta X minus delta U delta Y. So here V is the Y component of vector V, right? So this is that thing. Now if you define defining V U, the components, in terms of stream function, then you can write U is equal to delta psi delta Y and small v is equal to minus delta psi delta X, so that you can easily write divergence of V is equal to 0. So from here it follows that z is equal to, so this will be del v del x. Okay, so it's a scalar function, and if you do this, then this will be this. Okay, so psi is a function of x and y. So divergence of v, then it will be divergence of u, del u del x, that means delta psi del x del y, and del v del y will be minus delta psi del x del y, and that will be cancelled out, and that will satisfy this relation. So epsilon z, then it will be del v del x. So del x of v is minus delta psi delta x minus del y of u, it will be delta psi delta y. So that makes it minus delta psi delta x2 minus delta psi delta y2. That becomes Laplacian of psi. So let's say this is question number 6. And in the equation number 5 we got this. So from there we can write then Laplacian of this of Laplacian of psi will be 0. Okay. Okay. So now from this, so this is a coordinate system. So now if we take a different coordinate system, since we are talking about sphere, this will be for a different coordinate system. This will be this, right? So then the equation becomes, this is an operator, okay? This is not any energy or something like this. This will be 0. Okay. So let's assume like this. This is a sphere, and there are two things like this, and let's say this is z, this is r. Okay, this is r. This is r, like this, and this angle is theta. So now far away from the sphere, far away from the sphere, in downstream, in the downstream, so sphere will not have any useful contribution, or it is intuitive to note that sphere will not have any significant contribution in this. Okay, So now this is the direction of veer, and perpendicular to this will be v theta. So this is theta, and this will be u infinity. So if you take this, then Vr will be from these relations, then sorry, this theta. So this, from this relation you can write Vr is equal to u infinity cos theta, and v theta is equal to minus u infinity sin theta, minus u infinity sin theta. Okay, so now you can get some idea how to do this. So the Vr then will be 1 by r square sin theta delta psi delta theta. From there you can get u infinity cos theta at r tends to infinity, far away. So from here you can get, if you do the partial differential equation, is u infinity r square sin theta cos theta d theta. So from here you can get on solution psi is equal to u infinity r square sin square theta by 2 plus a function of r. That function of r you need to get later, because here you are getting the function of theta. Similarly, v theta is 1 minus 1 by r sin theta delta psi r is equal to minus infinity sin theta. From here you can get psi equals to u infinity r square sin square theta by 2 into f2 theta. So this was 7, this was 8, this was 9. So now you can easily write that, okay, sorry, some network issue. Okay, just a minute. So this is a rigorous calculation, so please be with me. So what we are doing was, we were solving this psi and we got this. So now we got this string function as u infinity r square sin square theta divided by 2 at r tends to infinity. Okay, so look at this result sometime. So for 1 minute please look at this derivation. Okay, so now if you want to get the theta independent term, you have to write these equations in a long form. So for that we will take help from vector calculus. Okay, so we know this equation, right? E square is the nabla, or sorry, Laplacian in the coordinate, so 0, and E square in spherical coordinate is this delta 2 del r2 plus sine theta by r square del theta of 1 by sine theta del theta. Okay, so if you do this, then calculating theta dependent term will be sine theta by r square del theta into 1 by sine theta del theta sine square theta. So we will take this sine square theta and fr. This is a fr. So sine square theta and this is f of r. Okay, so in the same way you can do this and you can get the this thing relation. Okay, so now you get this fr which will be equal to sine theta by r square del theta. So this sine theta, there will be 2 sine theta, 2 cancels out, this will be 2 cos theta, right? Del theta of 2 cos theta f of r, and this calculations becomes minus 2 sine square theta by r square into fr. So then your this relation becomes E square or Laplacian of psi for if there is fr, if you get it in this relation, so fr will be double derivative of r, so there will be f prime double prime minus 2f by r square, and sine square theta will be there. So we can write this thing actually like f of r sine square theta. Okay, so from here then we can write this as E square as g of r, this is a function of r only, g of r sine square theta, and now E square of E square psi which is equals to 0, that also you have to derivative like this. So there will be del of, so this per term will, only this term will be taking derivative, then this becomes g double prime prime r, and for the sine square theta part it will be minus 2gr by r square. Same, because the same logic we are using. There was fr sine square theta, here e square psi was gr sine square theta. So this will be sine square theta equals to 0. That makes it g double prime r minus 2gr by r square equals to 0. So now if you assume answers, so this is equation number 9. If you get an answers of f is equal to c of r to the power n, then f double prime becomes n into n minus 1 constant r to the power n minus 2, right? So if you substitute this value here, then gr then becomes gr, g of r is f double prime minus 2f by r square, which makes it c into, for first one is n into n minus 1 minus 2 into r to the power n minus 2, which can be written as c into n plus 1 into n minus 2. You can see that will be the thing in r to the power n minus 2. Clear? So now if you take g prime prime r minus 2g by r, which is equals to 0, that gives you, for g double prime prime r, so that gives you n plus 1, n plus 2, n minus 1, n minus 4 equals to 0. So the value of n will be 1, 2, 4, minus 1. This is n minus 2. So the solution then becomes f is equal to c1r plus c2r square plus c3r to the power 4 plus c4 by r. This is question 11. Now, since there are 4 unknown variables, so we need 4 boundary conditions. So, to get the stream function, we need 4 boundary conditions. That makes, so 2 are obtained from boundary of sphere, right? 2 boundary conditions, 2 BCs are obtained from boundary of sphere. How? One is, there is no slip and no penetration. Which is at r equal to capital R, which is the radius of this, psi must be 0. Psi must be 0, that means f of r must be 0. That means at r equal to r, delta psi delta r equals to 0, and from that del f by del r equals to 0. This r is the coordinate, spherical coordinate in the spherical space, and at r tends to infinity, so this is from penetration, and f becomes u infinity r square by 2, that we was calculated earlier here. Here we calculated here. So if that is the case, then from there we can get C2 r tends to infinity, that means this becomes 0, there will only 3 parts, so C2 becomes u infinity by 2 and C3 becomes 0, highest order dependency. Okay. Now from first thing at r equal to r, so this equation from 1 from, let's say this take not 1, this takes its I. If at r equal to r must be 0, that makes C1r plus C2, which is C2 is given u infinity by 2, so u infinity by r square by 2 plus C4 by r must be 0, and also df by r at r equal to r must be 0, and that makes C1 plus u infinity r plus minus rather minus C4 by r square equal to 0. This is equation A, this is equation B, or rather let number it I.1, I.1, this is I.2. Okay. Now if you multiply with r, then it becomes, or if you divided this thing by r, then it becomes 2C1r, or 2C1 is equal to 2C1 is equal to u infinity u infinity r by 2 minus u infinity r. That makes it C1 is equal to minus 3 u infinity r by 4. So this is I.3. So now we got 3 values. Now if that is, then C4 we can easily promptly get what is C4 will be. C4 will be then from these calculations, minus C1 R square. So this is in this relation. So if you substitute this value, C4 is minus C1 R square plus or minus rather U infinity R cube by 2, that makes it 3 U infinity R cube by 4 minus U infinity R cube by 2. So C4 becomes U infinity R cube by 4. So now you will get the string function appropriate full form f of r sine square theta, that makes it U infinity R square by 2 sine square theta into, first is 1, C1 is minus, so this will be minus 3r by r, 3 by r by r 2r, and this will be r cube by 2r cube. Okay. So now if that is the case, Vr will be 1 by r square sine theta delta psi delta theta. So that makes 1 by r square sine theta. So delta psi delta theta is only this value. So this becomes into U infinity r square by 2 into 2 sine theta cos theta into 1 minus 3 by 2 r by r plus r cube by 2r cube, sorry, rather. So then it becomes U infinity cos theta into 1 minus, so this sin theta cancels out, 2 cancelled out, r square cancels out, infinity cos theta minus 3 by 2 r by r. So this is a big calculation. You can see that we can easily write the Stokes drag, but this calculation is quite big and not tedious. Similarly, V theta will be minus 1 by r sin theta delta psi delta r, and that makes it minus 1 by r sin theta into U infinity sin square theta by 2, U infinity sin square by theta by 2 into first 2r second minus 3r minus r cube by 2r square, right? Okay, so this is, so now sin theta cancels out, so it becomes minus U infinity sin theta into 1 minus 3r by 2r minus r cube by 4 r cube. This is 4. Now we will use the Stokes equation. So Stokes, we have got the vector components Vr and V theta. So now Stokes equation was pressure was eta Laplacian V, because this was the equation, right? At the end it was the equation that was there, this one. Okay. Okay, so now if you get this equation and if you substitute the values, then you will get 1 by eta dpdr is equal to del 2 vr del r2 plus 2 by r del vr by del r plus 1 by r square del 2 vr del theta 2 plus cot theta by r square del v r by del theta. So this is a long calculation. I just want to write the expression 2 by r square del v theta by del theta plus v theta cot theta. Okay. So now if you get this, then this part and this part cancels out, right? So only thing remains is del p del r 1 by mu del p del r is equal to mu infinity. So this can be a good homework, cos theta 3r by r cube, and from here you get the equation of p as solution of p as 3 eta u infinity, or the cos theta into r divided by 2 r square plus p1. What will be the function of theta then? This is equation number 15. By the same thing, if you do, then 1 by eta r del p del theta, that becomes del 2 v theta del r2 plus, because you know here v theta is also r dependency, and 2 by r del v theta by del r plus 1 by r square del 2 v theta by del theta 2 plus cot theta by r square del v theta by del theta minus v theta by r square sin square theta plus 2 by r square del v theta by del theta. So by doing all these calculations, you will get del p del theta is equal to 3 eta u infinity. U infinity is the velocity at far away from the spherical sphere, a spherical surface, 2 by r square. From here you can get P is equal to minus 3 eta u infinity r sin theta or by 2r square plus p2r. This is equation 16. So from here you can easily write that P, comparing these two equations, P is P infinity minus 3 eta u infinity r cos theta by 2r square, where P infinity is ambient pressure. Okay. So this is the ambient pressure. Now if you talk about the viscous stress, the viscous stress tau rr is equal to 2 eta delta Vr by delta r, which is viscous normal stress, viscous normal stress, and tau r theta, which is eta r del r v theta by r plus 1 by r del Vr del theta, which is viscous shear stress. Okay. So now if you see a sphere like this, so fluid is flowing like this, let's say this is the center. Okay. So this is r, so this is r, this is r, and let's say if you consider a small portion like this, and this is theta and this is d theta, so this will be r sin theta and this will be r d theta. So tangential force will be like this, tau r theta, and this will be the normal force, which will be tau rr minus p. So if you calculate all those things, then surface area of this small strip will be 2 pi r with a, this will be a like this small strip, 2 pi r sin theta with the width like this, r d theta into r d theta. Okay. So this will be the A. So the normal force will be tau rr minus p into this A, and the tangential force will be tau r theta sorry, again, just a minute. There's some network issue. So basically, what we are getting, so this is tangential force, so this will be tau r theta into again 2 pi r square sin theta d theta. Okay, so if you take these two things, then you will get the expression. So this will be, you need to do the calculations as tau rr minus p cos theta minus tau r theta sin theta, because that will be, cos theta and sin theta component, and this will be around r equal to r, and this will be this a, and that equals to, now tau rr at r equal to r will be 0, and tau r theta around r equal to r becomes 3 eta infinity sin theta divided by 2r. So this drag force differential will be minus 3 eta u infinity sin theta divided by 2r sin theta plus p atmospheric minus 3 eta infinity r cos theta divided by 2r square cos theta into 2 pi r square sin theta d theta. So then it makes like this. So now if you calculate the fd mod of this, then if you calculate this integration, this will be d of d of 0 to r, and then it becomes minus 3 eta infinity by 2r sin square theta plus cos square theta plus p infinity cos theta 2 pi r square sin theta d theta. Okay, so again this part makes it fd makes it minus 3 eta u naught by 2r into 2 pi r square into sin theta d theta 0 to pi. So this becomes minus 3 eta u naught r pi into minus cos theta 0 to pi. Cos theta pi is 1. So if you take the mod of this, then it becomes 3 eta u naught r into pi into 2. 6 eta u naught 6 pi eta r times u naught. So this is the Stokes drag coefficient. So Stokes drag coefficient gamma is here this 6 pi eta r. And what is this negative sign indicates? So the negative sign indicates negative sign indicates it is opposite to the velocity, or it is dissipative, dissipative or resistive. Okay, so this is a resistive kind of force. Okay, so this is our long calculations. We'll stop here. We will resume our class the next day.